Hello everyone, my name is Emilios and today we're going to be talking about performance analysis on HPX applications using Traveler. To truly optimize an HPX application, we need to see the execution from the runtime's perspective. HPX manages millions of lightweight tasks on top of just a few hardware threads, and we need a tool that understands that distinction. This is where Apex comes in, the automatic performance environment for xScale. Apex integrates directly the HPX scheduler. It allows us to track the life cycle of every lightweight user-level task, recording exactly when they are created, when they are run, and when they are forced to wait. HPX exports this data in OTF2, a standard high-performance trace format. However, raw trace files can be massive and difficult to parse manually. This is why we use Traveler. Traveler is a visualization tool that turns those dense trace logs into an interactive map. It aggregates the data, allowing us to zoom in on specific task dependencies or zoom out to see the overall shape of our parallel execution. It gives us the visual context we need to spot granularity issues immediately. To use Traveler for performance analysis, you'll need the OTF2 library. To install it, you download OTF2 from the webpage score-p.org, configure it, and install it. You'll also need to build HPX with Apex. To do that, you should use the following flags while configuring. The flags are HPX with fetch Apex true, HPX with Apex true, OTF2 library true, OTF2 include dir, and just put the directory where you have installed OTF2, and that's it. So first, we will activate the Traveler environment by typing source and the environment file. Okay, now that Traveler is activated, let's use it for our first run, in which we are using the classic odd-even transposition sort. It's basically a parallel version of bubble sort. So the setup is that we have a loop that runs for n phases. Inside that loop, we check even indices in one pass and odd indices on the next. Using the HPX for loop, we're launching a new parallel execution policy for every single phase. This means that thousands of times per second we are forcing HPX to spin up threads, so let's run it. For this instance, we're going to use 4 threads, and when we run it, as you can see, Apex is on and creating these raw trace files. The application needs some time to run, so let's skip it and see how much time it require to fully run in the end. Okay, the run is finished, and as you can see, it took 74 seconds to run on 4 threads. From this run, a new directory was created called OTF2 archive, and this is where our trace files are saved. Now, using Traveler to visualize and interpret the trace files from our run comes in 2 phases, bundling and serving. There are 2 Python scripts in the Traveler directory called bundle and serve respectively that we're going to use. We use bundle to load the data into Traveler integrated from command line. To do that, I'm going to run the bundle Python script. Here we're just going to bundle the OTF2 traces and the source code file. For that, we're going to use OTF and OTF trace file and CPP since we're using C++. And we're going to provide the source file. Also, we're going to use the label sort suboptimized. For this, you can give whatever label you want to. So let's run it. It takes some time to run, so let's fast forward. Now that the bundle application has finished, I'm going to change the window and I'm going to go to the directory where I have Traveler installed, and I'm going to run the command serve.py so I can see my results. Basically, this is the serve application. We're going to wait a bit, and once we see serving on localhost 8000, we're going to head to a browser window and I'm going to type localhost 8000 and we get the interface. We press the button web interface, and here is where we have our analysis uploaded and the results. As you can see, I have already loaded the data. Here is the suboptimized tab, and as you can see, there are 4 tabs: utilization view, interval histogram view, dependency view, and aggregated Gantt view. You can actually select to see more panes like code and C++. you'll see the whole script that you run and various other selections, but for now I'm going to use these 4 panels that I mentioned. When analyzing performance, we must distinguish between algorithmic efficiency and runtime efficiency. In the previous tutorial, Vidhun correctly identified that our sorting algorithm was the computational hotspot, revealing the massive number of comparisons inherent to its large complexity. However, when we switch to Traveler to analyze the runtime behavior, we see a completely different and potentially deceptive picture. We're currently looking at trace data for the unoptimized algorithm. Surprisingly, the root to utilization plot shows a near perfect utilization score of 4.0. The graph is solid wall of activity, indicating that all 4 CPU cores were fully saturated for the entire duration of the run. This highlights the fundamental truth about parallel runtimes. Traveler measures how busy the cores are and not how smart the work is. The HPX runtime is successfully keeping the hardware saturated, but it's effectively running a busy full scenario where the CPU is working extremely hard on redundant operations. Drilling down to the task hierarchy allows us to map this behavior to our code structure. The utilization view for the sort and main body shows activity hovering near 0. This accurately reflects the role of our outer loop, which acts strictly as an orchestrator. It triggers a parallel phase and then idles while waiting for the synchronization barrier. In contrast, the helper view mirrors the full system saturation. This represents our inner comparison loop. Even though the algorithm is suboptimal, the parallel execution policy successfully generates enough concurrent tasks to fill the machine's capacity. Finally, the interval histogram clarifies how the runtime manages this massive workload. We see a distinct bimodal distribution. The sharp peak on the left represents the administrative overhead and spawning heads, and managing barriers between phases. The broader peak, centered at 1.5 milliseconds, represents the execution time of the task chunks. The runtime has automatically grouped the thousands of loop iterations into efficiently 1.5 milliseconds batches. This proves that while our algorithm is mathematically inefficient, the HPX runtime implementation is technically flawless, handling the task scheduling and load balancing so well that the inefficiency is hidden from the system utilization monitors. Now let's look at the optimized version. Notice immediately how much cleaner this is. We've completely removed that manual for loop and the complex odd-even logic. Instead, we're leveraging the HPX parallel algorithm library. We simply call the HPX sort and pass it to the HPX execution par policy. By doing this, we're handling full control over to HPX runtime. We aren't manually managing synchronization barriers or phases anymore. HPX will automatically partition the data, distribute the work across the available thread pool, and perform a highly optimized parallel introspection sort. So now let's run the optimized sorting algorithm. We do it in the same way. As you can see, the run is much faster, taking it only 0.4 seconds to run. And now we're going to use the exact same procedure to load the data onto Traveler using bundle and serve. As you can see, I have already uploaded the data, and let's dive into them. We see the results of replacing the bad algorithmic logic to a more efficient algorithm of HPX sort. The largest difference is not the intensity of the CPU usage, but the duration and the effectiveness. In the utilization view, we can see that the utilization climbs to a peak score of 4.0, confirming that the optimized algorithm is just as parallel as the previous one and fully saturates the hardware. However, the busy full scenario has been eliminated. The 80-second wall of redundant activity has collapsed into a sub-second burst of tense effective computation, proving that high utilization is only a meaningful metric when paired with algorithmic efficiency. In the dependency tree, we can see that the structural shifts are responsible for this dramatic acceleration. Where the previous analysis implied a rigid iterative structure dictated by global synchronization barriers, this new topology displays a clear recursive fork join pattern. The root node spawns dynamic branches that operate independently, visually demonstrating the divide and conquer mechanics of the underlying sorting logic. This structural change allows HPX runtime to process independent data partitions continuously, replacing the stop-and-go synchronization of the previous but sub-optimized sorting algorithm with a more fluid cascading workflow. And finally, the interval histogram confirms that the runtime's management of these tasks remains technically flawless. Despite the change in algorithmic structure, the distribution shows that the runtime continues to generate discrete, consistently sized execution chunks. The recursive splitting of the dataset produces tasks that fit efficiently into the thread pool. The thread pool's scheduling slots, maintaining the high load balancing we observed previously. This comparison proves that the HPX runtime provided a robust execution environment in both scenarios, but it requires a mathematically superior algorithm to translate that hardware saturation into viable application performance. Now I've been using Traveler because it's specifically designed to visualize the task dependency chains in HPX, but Traveler isn't the only tool capable of reading these O2F2 trace files. If you're working in a professional HPC environment, the industry gold standard is Vampire. It handles massive trace files comfortably and provides the incredibly detailed, but it does require a commercial license. For a free open source alternative that runs right in your browser, you can use Perfecto or Google Chrome tracing. Typically, you would need to convert the O2F2 files into a JSON format first. However, since you are using Apex, there's a shortcut. You can configure Apex to export into Google Traces by setting Apex Google Trace equal to 1 instead of Apex O2F2. This keeps the middleman out and generates a file you can drag and drop directly into the UI perfecto.dev to see your thread timelines immediately. Finally, if you don't want to look at graphs and you just want a tool to tell you where the problem is, there is Kalaska. It analyzes the O2F2 file and automatically flags bottlenecks like late sender or wait states, without you having to hunt for them manually. So that was the tutorial for performance analysis with Traveler. See you in the next weeks with another tutorial. Happy coding, everybody.